Hi there, welcome back to another video. Today I wanted to take a look at the rates of reaction question from this paper, and specifically one of the questions could easily catch you out if you're not careful. Let's take a look and go through some of the answers. So the question begins with the reaction between pure aluminium solid and excess hydrochloric acid HCl is used to investigate the factors that affect the rate of a reaction. The balance equation for the reaction is, and they've given that to us. Then they give us some information about experiment 1. They tell us that in experiment 1, 1 mole per dm cubed of HCl solution reacts with a 0.5 grams aluminium strip from an aluminium roll at room temperature. The graph of volume of H2 gas versus time for this experiment, not drawn to scale, is shown below. Now H2 gas is the product, and they've plotted the volume of H2, or the volume of product that is forming as the reaction progresses. Question 5.1.2 reads, for the time interval t equals 0 to t equals 5, the average reaction rate for the formation of H2 is 0,033 dm cubed per minute. Calculate the mass of aluminium present in the container at t equals 5 minutes. Take the molar gas volume as 24.5 dm cubed per mole. Now, to answer this question, this is a 6-mark question, so it's going to be multiple calculations. So we'll start with the rate. We've been given the rate of the reaction, and so we'll start with our rate formula. 5.1.2 rate. In this case, we get the formula from the units. dm cubed is a measure of volume divided by minutes is obviously time. Now they've given us the rate 0,033 equals the volume divided by, and the time is t0 to t5, so that is a total of 5 minutes. Now we can calculate the volume by cross multiplying. The volume is equal to, let's multiply here, 5 times 0,033, and that's equal to 0,165 dm cubed. And let's just make sure that we write out exactly what this is. This is 0,165 dm cubed of hydrogen gas produced in the 5 minutes. And it's always, I just always think it's a good idea to write it out, though it's not necessary at all the time, but write it out so you have an idea of exactly what's happening. Now, they tell us the molar gas volume. So we can calculate the number of moles. So that was step 1 if you want. Then step 2 is going to be number of moles equals V divided by Vm. That's equal to 0,165 divided by Vm, 24.5. And that gives us an answer of 6,73 times 10 to the negative 3 moles. Again, what is this? This is the moles of H2 produced in the 5-minute interval. Now that we have the number of moles, we can do a mole ratio to get the number of moles of aluminium. So step number 3 here, we'll say the mole ratio for aluminium to H2 is 2 to 3. Now we don't actually have 3 moles of H2, we have 6,73 times 10 to the minus 3, and then we can call that x. Now if you want x, let's cross multiply here. So 3x is equal to 2 into 6,73 times 10 to the minus 3. That means x is equal to 2 over 3 times 6,73 times 10 to the negative 3. Now, this is not actually necessary to write it out like this. I'm just showing it to you because it is an option. So that is now x, and then multiply this by 2 over 3. That gives us 4,49 times 10 to the negative 3. Now, what is this? Remember, we said that this is aluminium. But this is not going to be aluminium that's formed. This is going to be aluminium that's used. So moles of aluminium used in the same 5 minutes. Okay, now that we know the number of moles of aluminium used, we can convert that to a mass. So we'll say that the mass is equal to the number of moles multiplied by the molar mass. So 4,49 times 10 to the negative 3 multiplied, and let me just get the molar mass of aluminium. The molar mass is 27. So multiply that by 27. That gives us 0,12 grams of aluminium used. So they want to know how much of aluminium is left over. So left over is going to be, so point number 5 now, the leftover amount is going to be how much we started with. They told us that we started with 0,5 grams. So 0,5 minus the amount that was used, 0,12, and that gives us 0,38 grams. So if you break it up into steps like I've done here, it does become a bit more manageable, and writing out exactly what you've got, what you've calculated, also generally does help. Like I've done here, like just making these little notes for yourself really does help. Okay, now let's move on. Next question reads, assume that the concentration of HCl stays constant for the duration of the reaction. Use collision theory to explain the change in reaction rate. So they want to know, why does the graph look the way that it does between 0 and 5? So why is that gradient getting less? And so we can explain it by looking at what's happening to our reactants. Remember, as a reaction proceeds, the amount of reactants that's there decreases. So it'll be easier to explain using aluminium because aluminium is a solid piece. So we can say that 5.1.3, we can say during the time interval T0 to T5, right? The amount of aluminium decreases. Since the amount of aluminium decreases, there's going to be a smaller surface area. And remember, if there's a smaller surface area, there's going to be fewer effective collisions per unit time. And that means that the reaction rate will decrease. Okay, experiment 2. So experiment 1 is repeated using 2 moles per dm cubed of HCl solution. 5.1.4, redraw the above graph, no numerical values needed, in your answer book and label the curve A. On the same set of axes, draw the curve that will be obtained for experiment 2. Label this curve as B. Now, a number of people, when they see this question, they would think that because there is a greater concentration here, that we're going to produce more hydrogen gas, right? And that would make sense because you have more concentration, you have more molecules, and you'll get more hydrogen gas. That's what you normally would assume. But we need to be careful. And the reason why is because, remember, at the beginning they tell us that the HCl is in excess. And so remember that the amount of product formed isn't dependent on the excess reagent. Rather, it is dependent on the limiting reagent. So even if you increase the concentration of the HCl, since it's in excess, the volume of H2 gas that's formed isn't going to change because it's the excess reagent. However, since the concentration has increased, the rate will increase, but the amount of HCl, the amount of hydrogen gas that's produced is going to remain the same. So what will the graph look like? So the graph, let me use a different color here, is basically going to bottom out or flatten much quicker, but it's going to reach the same level. So let's go with something like that. Right? So just to show that the amount of H2 is going to remain the same because HCl is an excess reagent. Okay, and here we can see that the graph flattens earlier, meaning that the rate is quicker. Okay, and let's move on now. Experiment 3. Experiment 1 is repeated using 0.5 grams of pure powdered aluminium. So remember at the beginning they tell us that experiment 1 was done with an aluminium strip. Now they repeated the experiment, but now they've used powdered aluminium. Okay, so alluding to the state of division here. But let's look at the question. The question reads, how will the volume of H2 produced compare? Okay, so again, they're trying to trick us. The examiners are trying to trick us. So the state of division will affect the rate. The state of division will affect the rate, but it will not affect the amount of product that's formed. Because remember, the mass is still the same. So using powdered aluminium isn't going to make more H2 form. Rather, it's just going to increase the time at which it forms. So it's going to increase the rate. Okay, so the answer here is equal to. Question 5.2, curve X is the Maxwell-Boltzmann distribution curve for a reaction under a set of reaction conditions. A change was made. All right, so X was the original and then Y is the change. What change was made to obtain curve Y? Okay, so it's pretty easy to identify here because remember, if you look at let's interpret this. The peak for X is there. That means most particles will have, say, this kinetic energy here. Right? Now, the peak is here. So you can see that the kinetic energy increased. So EK for most of the particles have increased, right? Now, the reason why the kinetic energy would increase is because the temperature increased. Okay, so when you're looking for these Maxwell-Boltzmann curves, look for the peak. If there's a shift in the peak, then that's more likely an indicator that the temperature has increased. Okay, and we've given the reason. Okay, that's it. Hope you found this useful. If you did, please leave a like, share, subscribe, hit that bell icon for more videos. If there's something specific topic, specific paper, specific subject you'd like me to help you with, let me know in the comment section below. And until the next one, bye-bye.